Hello, I'm Ang from Tokyo Institute of Technology. In this presentation, I'd like to introduce an FPGA-based stochastic SAT solver leveraging intervariable dependencies. In IoT systems, the control rules are often representable in the Boolean SAT problems. This motivates us to develop a SAT-based controller for IoT systems where real-time processing is required. Recently, hardware SAT solvers have been developed, but they mainly evaluate on randomly generated SAT instance without considering features in realistic problems such as intervariable dependencies. We measure the number of dependents each variable has in two different SAT domains of same variables count and found that IoT instances have lower dependencies than random. Therefore, we would like to utilize this feature in accelerating solution search in SAT solvers. In this work, we have two main contributions. Firstly, we propose a simple yet effective technique to analyze the intervariable dependency of SAT instances and explore good setting of stochastic parameters based on their dependencies. Then, we apply the explore parameters into the configurations of our work Amoeba SAT, which achieve best performance among hardware SAT solvers to accelerate its solution search. Our baseline is Amoeba SAT solver, a stochastic SAT solving algorithm inspired by an amoeba. This solver features high parallelism, that it explores the assignment of all variables in parallel. For example, consider a Boolean function of 4 variables as follows. To explore for its solution, the amoeba SAT solver constructs a 8-unit system where each variable xi is determined by a pair of contradictory units. Each unit is associated with some intermediate variables representing the amoeba's natural features. During solution search, all units update their assignments in parallel, and a solution is converged after some iterations. We focus on a feature of SAT instances, intervariable dependency, which represents the level of influence a variable has in SAT instance. This is measured by considering two types of relations. Direct dependent refers to variables within the same clause, and indirect dependent refers to variables from different clauses, as seen in these two example clauses. In this SAT instance, the unit not x4 is found to have highest number of dependents, meaning it has the highest influence on assignments of other units. Based on the difference in units' influence levels, we propose a leveraging scheme for intervariable dependency through a stochastic parameter epsilon. Epsilon is used for random fluctuations in each unit of amoeba SAT, which is shown in the formula. It represents the probability of unusual behaviors in a unit, where the higher epsilon is, the more chance that variable changes its assignment. We consider that if a variable unit has low dependency, epsilon needs to be larger to help escape local optima. On the other hand, for the higher dependency units, epsilon should be smaller to make the assignments stay close to global solution. In our procedure, from the input SAT instance, we analyze the intervariable dependencies by each unit and classify them into different levels. Then, for each level, we explore the tuning set of epsilon to be used. Then we configure the hardware with tuning epsilon setting for implementation. We target FPGA with architecture shown in the figure. For each processing unit, the intermediate variables are updated in a pipeline manner. We design by high-level synthesis. For usage in pre-process, we generate the predefined rules for the solver and explore tuning epsilon for each unit. Then in solution search, the units will continuously run to search for different solutions. In our experiment, we consider two groups of IoT-oriented SAT benchmarks: graph coloring problem, GCP, found in IoT scheduling, and block score, BW, found in planning applications. We compare between our previous work, hardware amoeba SAT, or baseline, and our intervariable dependency aware implementation, ours. We firstly analyze the features of two subdomains regarding the average connections or dependencies count per unit. We found that GCP has sparser dependencies while BWs are denser due to higher average connection count and deviations. We then explore the tuning epsilon values for each instance and utilize two-level epsilon. We found that in GCP, the epsilons are similar among instances, but in BW, the gap between the tuning parameters becomes smaller when instances become more complex. With a two-level epsilon, we compare with baseline and found that ours achieved significant speedup by iteration reduction on average of 2.47 times. In addition, for the largest sat instance in BW, huge, baseline time out, while ours can converge to a solution in a reasonable time. This table shows the hardware implementation results. For slice count, it is seen that baseline makes smaller slices on most instances, but ours just creates up to 5% overhead. For clock speed, ours even achieve better clock in most instances, meaning ours creates almost no effect on hardware implementations. In conclusions, we have proposed a simple yet effective technique to accelerate solution search in SAT solvers considering intervariable dependencies. We achieve significant speedup over baseline with almost no effect on hardware implementation. For future work, we will explore more schemes for variables classification and try this technique on other stochastic SAT solvers. Thank you for your listening.